Okay, hello again. Sorry once again for any delays between the last and now. Really, let's see, 5 people are able to follow the last 2 videos. Now, looks like they've cleaned this up, haven't they? This is different from now than before. It's quite nice. Yeah. I changed this button. Anyway, getting on to where we were, there was one more example I wanted to show you to do with set jump and long jump. It's taken directly out of the helpful hint file from here. This example. So I'll just run through this example exactly as it is without much explanation. More explanation could be given on this line, which is crucial. Right? None of this would work. But let's see anyway. Okay, now the idea is we come in here and the comment says unmask all floating point exceptions. Now the way this function works is it takes a value and a mask, and what it does is it sets every bit in the mask equal to the corresponding bit in the value. In this case, the values bits are all 0, and the mask is 8001F. So these 6 bits will be set to 0, and those happen to be the ones that need to be set to 0 in order to enable exceptions when the exceptions that correspond with those particular bits happen. That includes pretty much all floating point exceptions, I believe. Although they're bundled, the actual codes themselves are bundled up into these numeric values that don't really coincide with the mask. So anyway, let's have a look at the help here on this for a second. Right, this is the function you're supposed to use, but whatever. We control word bits to set. Now there's something on the floating point unit, which is another processor on your chip. Usually they used to call a math coprocessor, which deals with floating point operations. Mask or unmask exceptions. Okay, now when we set the value to 0, I believe that unmasks an exception. If the value is equal to 0, if the value for mask is equal to 0, not in this case, gets the controller. Otherwise, if non-zero, a new value is set. For any bit that is on in mask, corresponding new bit in new, that's this, 0 in our case, is used to update the control word. On the unit, there's something called MCW, I think. MCW. Now, I don't know what the M stands for, but I think this is control word. Maybe math or something. Math control word. Or mask. Right. Well, I know that this is turning them on, so obviously a value of 0 means on. Let's just verify that. If possible. This is something else. Here's the interrupt exception mask. Okay. These are the bits that we're setting to 0. So those bits, these control interrupt, an interrupt from escaping or not escaping the processor. And obviously a value of 0 means that it's going to get out. Where does it say that? Oh, 0. If the value of 0 is passed through what? This is talking about when you have 2 floating point units. Mask new is used. Well, we can test it if you want. The first here, I'm going to divide 1 by 2, right? And that would be a divide by 0. So what if we set that bit to 1 instead of 0? Okay, how do we do that? What would correspond to here? 0 divide is 8. So we want the value, okay, that's included in this, and put an 8 here. That means it's going to set the 0 divide line, its interrupt line, value to 1, and the rest will be 0. So that would mean that this one should not cause an exception. It's the next one. N1 times N2 does not look like an exception will occur, but I know how to make an exception occur. Believe it or not, this causes an exception for any values, I think, unless they're powers of 2. So they should cause an exception. Trying to, you see how this thing works, right? It's going to take everything from mask here, which is certainly includes this. Oh no, doesn't. Yeah, it includes that bit. Yeah, right, for the low nibble. And the top bit of the low nibble is being set to 1 and everything else 0. Of these bits, which are the ones to deal with interrupt. An interrupt being thrown due to one of those signals, one of those operations, errors occurring. Okay. Now the call here, signal, which I've written down the helpful one here, sets a function, a handler. This is just like this just sets a function handler for the given type of exception, in this case floating point exception, to this. And it turns out that the handler itself takes two arguments, and it's documented in the help that for floating point argument, a second parameter is passed, and that tells you what type of error occurred. Okay. However, the function signal itself, it doesn't take signal function. It expects a function that is a void function taking just one int. Okay, now we have in brackets maybe more ints, but I don't know how to specify that. So we just cast it to a function that takes an int. And now, just like before, setjmp, mark, print the context like before. I added a couple of things here. And we're going to divide 5 with 0. Now, this should not cause a pivot. Okay, so the answer R is, it came out to infinity. This stands for infinite. Okay, now this should do it, believe it or not. It didn't. What am I doing? Oh, 0. It's bigger than 0. Let's try it. Yes, I think this will do it. It's just something I found out just when I was just playing with this code. I was trying to remember how you do powers, and the power sent me off in the, it worked. Now it's working. Oh, 5 to the 0. And 2 is 0. Yeah. And 1 is fine. N1 to the N1. N1 to the N2. So the message is not correct. There, see? Now that's just 5 to the 5, which would have given me, 5 to 5. But instead, that gives me an error called inexact. So again, we certainly wouldn't want to be trapping that, right? You want 5 to the 5 to work, even if the answer is not precise. I tried changing the properties from precise to different things, like fast and so on. That didn't help. It's because we're asking it to generate an exception on an imprecise, an inexact exception. That is, I don't know if you know how floating point numbers are represented in floating point format, but even, I don't know, we can even do the number 5, just to the 1 won't probably give us inexact. So we can represent 5 exactly. Yeah. See, the way it works is, at least for single precision, let me pause for a second. I'll try to work out a quick way to explain why this is inexact. I don't know. It's okay with 5 times 5 and 5. How 5 to the 2? It's not okay. I don't see why. Yeah, anyway, stepping through it always ended up on a line saying, have error in power. So there's something different about this to 5 times 5. I mean, it's using a different approach to do this raising to the power. And I don't know why, but whatever algorithm it uses, it's not able to represent, I guess, the exponent as a finitely represented number in terms of powers of 2. Also fractional powers of 2. So anyway, I turned that one off. Another way to turn one off is, well, one, we could do it by just adding that one to here, which is a 1. So we could say 9. And that should turn it off, and that should allow this POW, which we could do first. Well, both of them should be okay. And not end up in this handler that we set up. That's fine. Infinity, no problem, right? I was looking at some of these registers, and at one point this had a weird value in it. So now the only thing I wanted to point out about this, it's using setjmp and longjmp, according to the help anyway. There are 2 ways to handle floating point exceptions. One is this way, another is to use try except. If you use this method, you have to be very careful, because the signal handler routines are usually called asynchronously. When an interrupt occurs, the handler may get control when a runtime of operation is incomplete or in an unknown state. For instance, you might be calling printf, and by a mistake, where you specified %f, you may have put the wrong argument in your argument list or something like that, and this thing gets entered, and you're in the middle of printf. So you're not supposed to do any of these things during your handler. No low-level I/O routines, no heap routines, right? Don't use any function that generates a system call. Things to do with time, get something. I don't know what that one is. And don't use longjmp unless it's a floating point exception. So that's the one exception, and that's what we're using, longjmp. And in this case, first you have to reinitialize the floating point unit. We'll call to FP reset. It's not emphasized in the example that this is not a maybe thing. This has to be done. And I don't know what this last one is. I don't know what an overlay routine is. But there you go. That's how you set the mask, floating point interrupt mask. Now another way I could have done that last bit, if I didn't want that thing, is I could have removed from this mask the inexact. So I could have ended this with the not of inexact, and that won't be in the mask. And I could similarly do that with this 8, which was divided by 0. So I could take these two and combine them, flip those bits and that together, and that should have the same effect, allowing both types of exceptions through. That is, they won't generate an interrupt. An interrupt just means that the processor is called back on. See, we managed to get through that, and we managed to get through the POW. But we won't manage to get through this one. This is, you might think, a division by 0, but it generates a different exception, and this one should definitely get us into our set jump, and it does. And the error is, we'll print it out. I haven't printed it out yet. Can't do any printing in the handler, but we can print it out now. That error is not a number. This is not. It's this printout as well. It should be 0 by 0. 0 over 0 is not the same as division by 0, and in fact, at one point it was the same with the version up to version 7 of this compiler. This would give you an infinity result, and that is not conforming with the standard, the ANSI C++ or C standard. This operation is not supposed to return infinity as a result. It's supposed to return. The result is supposed to be what they call a NAN, N-A-N, not a number. Now, there's a major difference between those two, and you can imagine that it's like a friend of mine said once, that people were all worried about the year 2000 switch, right? When maybe things going from two-digit years to 4-digit years that might cause the end of the world. Well, if you want to talk about a major switch in computing, it was when this compiler changed to being compliant, and when this sort of thing stopped returning infinity. I mean, you can imagine, you got your little nuclear power generating station that if the temperature goes up too high, then it quits its loop and starts shutting down the reactor. Well, suddenly all of the logic changed, right? Like, who would have known possibly that denominator became 0, and so a comparison became true, like temperature is above a certain value. If you compare something like go here, somewhat clean. It's just some number, 1.6. Okay. And this one that is 0. Let's say, well, here's our reactor. Reactor num. It would be num. And the numerator is usually a number like 4, right? And in your code you have, core temperature, or you might say if this value, or the numerator over the denominator, who knows what the calculation is? How can I press a key? Something like that. Shut down reactor. Something like that. Some big calculation, and you can see that certainly if it divide by 0, that should become a true statement. It's going to be bigger than that. It's infinity is bigger than every number. Unless it's negative infinity, then it's less than every number. So that should return true, and reactor shut down. Prior to version 8 of the compiler. Well, and version 8 in this case. Come on. Okay, now is that true? Yes, so shutting down the reactor. However, it turns out that this here became 0. Okay. You have a big long calculation, and it turned out that this happened. Well, we don't shut down the reactor in that case. Everything's fine. Well, everything's not exactly fine, right? Everything's gone wrong. We've got 0 over 0, and we don't know what's going on. And worse is this would also return false. Every comparison that you make with man is false. Equals false. So if you were relying on some condition becoming true to shut down your nuclear reactor, and it involved floating point numbers, well, if a nan ever got in there, then nothing can be equal to true, ever, right? But the world did survive that change to 2 points, so we're all alive and we're all happy. And how much time have I wasted? Not too much. I wasted a lot of time trying to figure out why that POW gives us inexact. That has to do with the details of that particular function. it's nothing to do with 5 times 5 being inexact. In terms of how you represent the number 5 in floating point, well, in single precision, 5 in no single precision, it's easier. 5 is simply 101 in terms of powers of 2, right? Right? Okay, now in terms of the way the floating point unit represents numbers, again, single precision, which is 32 bits. All numbers are of the form 1.xxx, however many digits are possible, and then times 2 to the power. If you're allowing for negative numbers, which usually you are, it's what they call the biased exponent minus 7f. Okay. Now e is a number that's stored. Okay, and also these x's. This needn't be stored because it's assumed to be there all the time. And same with these. So it's just this and these x's. Okay. So what about 5? Well, 5 here is 101. So if you divide by 100, then we have 5 equals 1.01 times 100. 100 is 2 squared. Okay, speaking binary 100. Whoops, 1.01. Right? Because I divided by 100, so the decimal point moves over 2. Now 2 here is 81 minus 0x. Okay, so the numbers stored are 81 and 01 plus a sign bit. The first bit is a sign bit, 0 for positive, center of it. The next 8 bits are the exponent, which is this bit, the biased exponent. So that's 81, that's an 8, that's a 1. Biased exponent. And then the remaining bits are these x's, 0, 1. And however far you can go. The rest will all be 0. Now, I won't group these because this is already not grouped into nibbles. Putting it together, now I'm going to take that away to avoid confusion. There we go. And it's 31 bits. That's it. 32 bits. 1, 2, 3, 4, 1, 2, 3, 4. So there is the number 5, 0x, 4, 0, a 0, 0, 0, 0, 0. So that's number 5. in single precision, that's as a float. Okay, now for a double, it's twice as many bits, so you get a much larger possible exponent. The largest possible exponent is 2 to the 127 or 128, depending on how you look at it, in single precision, and you don't get very many bits for what they call the mantissa, I think. This part, the part that starts here. That's how many bits you get for your number part, the digits. Okay, so and there's maybe I should make a reference for it, but it's a crash course in converting numbers to floating point. Now, not all numbers can be represented in a finite number of bits, but that's not the problem with 5 or 25 or whatever. Okay, 5 can be represented exactly in powers of 2 in that format. Any integer number can, but not every number. This is an example given here. This number won't work as a finite. It won't be, and that's what I thought was happening, that maybe it wasn't finitely represented, but it can't be. This 0.27 is a problem, and you get a repeating thing. Anyway, so that's that. I don't know. I guess I'll just let this be the end of the set jump long jump. I'll show you C++ exceptions. Very simple concept, and then we'll go on to more interesting stuff. One of the things, just if you're curious, as I'm printing out using these print contexts, I added some into the print header. We'll look at that another day. I should add a reference to the floating point. The linear address of the thread information block, you probably still have it in memory. It's always the same number. Now that first frame or whatever was 1 to F70. You can see it's actually at the head of the block. There's nothing below this or above this thing. Some stuff above, not much, I guess. This number is outside any module. The highest it goes in terms of modules is 7. That's 7F. And if you keep dereferencing this, eventually you get to -1. What I do is put this crane thing into the variable, and I just kept starring it until I hit. Turns out I hit -1, and there are two things. Turns out in the list, and we'll get to what those are later. And this linear address is the same as fs:0, obviously, with the number. What the rest of these are, I don't know. They look like addresses. At this address, 1 to FF70, there should be at least a function pointer. Let's see. Well, this here, the first 4 bytes is the next thing in the chain, and this here should be a function pointer for to B8 and I don't know what that is, but I know that there's at least that the spec says that there's at least a next pointer and a function pointer, and then the rest is OS specific. This one here is a try-level thing that we picked up somehow. Okay, I'll leave this here. I'll go on to the next shortly. See you.